Hello there, and welcome. I'm glad you've wandered here tonight. Maybe after a long day, maybe chasing a quiet thought that wouldn't quite let you go. Whatever the reason, you've arrived in a calm corner of the universe. You don't need to do anything now but rest. Let your breathing slow. Let your mind drift loose from gravity. Because tonight, we're going to the edge, the very brink of space and time itself. Beyond the last stars, beyond even light's return, there lies a boundary called the event horizon, the place where falling never stops. Past that veil, reality folds inward. Time stretches thin. Space curls into silence. At the center waits the singularity, a point so dense, so strange, that the known laws of physics bow out and whisper, "We don't know what happens next." This is not a nightmare. It's a lullaby for the curious, a slow dive into the dark heart of the cosmos, where mystery hums, where gravity sings, and where the universe keeps its deepest secrets. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Imagine a place where light forgets how to leave, where the fastest thing in the universe, the very messenger of sight itself, hesitates on its journey and begins to curve back on itself. That place is the event horizon, the invisible boundary around a black hole where gravity's pull becomes absolute. It's not a wall or a solid edge, but a threshold drawn by space and time conspiring together. Cross it, and escape becomes impossible, not because something stops you, but because every possible path now leads inward. Even the road called out turns back on itself. If you were to drift toward this boundary, you would never notice the precise moment you crossed it. From your own perspective, nothing special would happen. You'd see the stars ahead, the black void behind, the same silent drift forward. But to someone watching from far away, you would seem to slow down. Your image would stretch, your light reddening, dimming, until you froze just above the horizon, motionless and fading, like a candle seen through endless fog. To the outside universe, you would never quite disappear. To you, the rest of existence would vanish in a single blink. Light itself behaves strangely here. Normally, it travels straight and steady, indifferent to distance. But near a black hole, space itself is curved, and light bends as if drawn along invisible rails. It tries to climb out, but gravity slows its climb until it can barely crawl. Imagine a mountain so steep that even light tires before reaching the summit. At the horizon, the slope becomes infinite. Climbing becomes falling. The light turns inward, surrendering to the curve that once only nudged it. The event horizon isn't a thing you can touch. It's more like a moment in time that keeps moving, a place that shifts depending on who's watching. To the universe beyond, it's a surface of no return. To what lies inside, it doesn't even exist. There is no edge in there, only direction, forward. And forward is always toward the singularity. It's a border defined not by matter, but by perspective. Scientists call it the point where escape velocity equals the speed of light. That sounds clinical, but in truth, it's poetic. The universe has written a limit into its own rules. Nothing can move faster than light, and here, that speed is exactly the price of freedom. The horizon is the place where the cost becomes too high, where the balance tips and all movement points inward. It's the final calm before descent. If you could hover just above it, though no ship or shield could truly hold you there, you would see the sky wrapped around itself. Starlight from behind would bend forward, circling the whole like ribbons of fire. The entire cosmos would appear compressed into a single glowing ring, a halo of every color and every distance merged into one trembling edge. Behind you, there would be nothing at all, not black, but absence, a silence so complete it swallows even the idea of silence. The horizon is not death. It's not even destruction. It's a transformation. Matter that crosses it continues, falling deeper into curved time, into a geometry where cause and effect trade places. To fall beyond the horizon is to move toward the singularity as surely as an hour moves toward the next. There is no turning back, not because of force, but because the concept of back dissolves. What we call the boundary is really our limit of vision. We see a circle of darkness surrounded by light, but what we're seeing is the last cry of photons that almost escaped. The event horizon marks the end of visibility, not existence. Inside, the story continues in a language we don't yet understand. Outside, we are left with the glow at its rim, a reminder that even in the deepest gravity well, light resists for a moment, holding the line before it fades. Somewhere, right now, countless stars orbit these invisible hearts. Their light twists and bows as it grazes the horizon, painting thin arcs across telescopes and memory. Every orbit, every flicker, is a conversation between freedom and surrender. The event horizon is the pause between them, the breath before the fall, the border where the universe exhales and says, quietly, this far and no further. Time, we like to think, moves evenly for everyone. Seconds stack neatly, one after another, and the rhythm of life feels steady enough to trust. But near a black hole, that rhythm begins to bend. Einstein taught us that gravity isn't a force pulling things down. It's the shape of space and time itself. The stronger the gravity, the deeper the curve, and the slower the clock ticks. At the edge of a black hole, time becomes so distorted that what feels like a heartbeat to you could stretch into eternity for someone watching from afar. Imagine standing on the deck of a ship that hovers just above the event horizon. You look down at your watch. It ticks normally, calm and consistent. The seconds feel no different. But if you glance outward toward the stars, their light flickers strangely, as though it's breathing slower than before. To those stars, to the distant universe, your motion has nearly stopped. Every gesture you make, every blink, appears suspended. You could wave forever, and no one would ever see your hand finish the motion. The closer you drift, the slower you seem to move, until even your final heartbeat looks frozen in place. It's not an illusion, not in the usual sense. The fabric of reality itself is stretching beneath you, folding in ways that make time unequal. In deep gravity, space curves downward, and time curves with it. To fall toward a black hole is to fall through time as much as through space. It's a slow dance, graceful and unstoppable, where one partner, to the universe, keeps moving, while the other, the traveler, seems to stand still. From your own perspective, nothing has changed. Your pulse stays steady. You breathe in, breathe out. You glance at your watch again. It has ticked forward exactly as it should. But if someone were watching you from far away, they would never see you cross that last invisible line. They'd see you stretched thinner, slower, dimmer, until you faded completely. To them, you never fell in. To you, you never stopped falling. Einstein called this time dilation, and it isn't limited to black holes. Even here on Earth, your feet experience time a little slower than your head because gravity is slightly stronger closer to the ground. The difference is microscopic, but it's real. Atomic clocks have measured it. Near a black hole, that gentle slope turns into a cliff. The difference between one step and the next could be centuries. Think of time as water flowing across a landscape. In the calm stretches of space, it moves smooth and fast. Near massive objects, it pools and eddies, thickening around them. At the edge of a black hole, it freezes entirely. Not because it has ended, but because it's fallen so deep that escape would require faster than light motion. Time, like light, can't climb back out. It becomes trapped, still moving, but only inward, toward the singularity. If you could somehow observe yourself from both sides, from above and within, you would see a paradox. The falling version of you would watch the universe race ahead, stars aging and dying, galaxies colliding, epochs passing in moments. From the outside, the stationary you would hang forever on the brink, never quite finishing the fall. Each version of you would insist they were right, and both would be. It's a humbling thought. That time, which feels so personal, is not a constant rhythm, but a shifting current, shaped by where you stand in the universe. The ticking of your heart, the length of a sunset, the patience of a thought, all depend on how space is curved around you. In that way, black holes are less like monsters and more like mirrors, showing us that what we call now is not universal, but local, fragile, and fleeting. At the event horizon, the slow dance becomes infinite. The music of motion fades, stretched into silence. And yet, inside the horizon, time continues its quiet measure. The traveler never feels the stop. They simply fall deeper into a place where every moment folds into the next, seamless and endless. For them, the universe outside has already aged beyond recognition. For us, they are still falling, eternally caught between seconds. Time doesn't die there. It just learns to move differently. Gravity doesn't shout. It never flashes or burns or roars. It speaks in curves, in the soft bending of space and the slow choreography of motion. Every orbit, every fall, every drifting leaf is a reply to that quiet voice. Einstein was the first to understand that gravity isn't a tug or a dock, thread pulling downward. It's the shape of the universe itself. Space and time weave together into a fabric, and wherever mass gathers, it presses gently into that fabric, creating valleys. The sun makes one. The earth makes a smaller one. A black hole makes a well so deep that not even light can climb back out. Imagine space not as emptiness, but as a surface, smooth, endless, invisible. Drop a marble on it, and the marble makes a dent. Now roll another marble nearby, and it curves around the first, tracing a circle. That curve is what we feel as gravity. It isn't that one marble pulls the other, it's that the surface between them bends, whispering the path each must follow. In this way, motion is not commanded but guided. The planets move not because they are forced to, but because space itself tells them how to move. In the presence of a black hole, that surface folds almost completely in on itself. The valley becomes a funnel. The funnel deepens without end, and the geometry begins to defy our language. The black hole is not a hole in the ordinary sense. It is a region where space turns inward, where every direction points to the same destination. Even the idea of down loses meaning. There is only toward. Einstein's equations describe this perfectly, though their simplicity hides their power. They link matter to geometry, saying in essence, mass tells space how to curve, and space tells mass how to move. It's a conversation that has been happening since the universe began. When a star dies and collapses under its own weight, that conversation becomes intense, intimate, unstoppable. The curve grows sharper, space folds tighter. Eventually, the fabric itself gives way to something we cannot yet describe, a point of infinite density, where curvature becomes absolute. To visualize it, imagine laying a heavy sphere on a rubber sheet. The sheet dips downward, and anything that passes nearby slides inward. Now, imagine pressing that same sphere with unimaginable force until the sheet tears into a funnel that has no bottom. The tear doesn't lead anywhere. It simply continues inward, endlessly. That's the geometry of a black hole. Not an absence, but an excess. Too much mass, too much curvature, too much reality in one place. But the beauty of gravity is not only in its extremes, it's in the way it shapes everything, quietly, patiently. The orbit of the moon, the fall of rain, the slow drift of galaxies, all obey the same equations. Gravity's voice carries across scales, from the gentle pull between atoms to the collapse of entire suns. It is the soft hum beneath existence, the structure that holds everything in place while allowing it to move. If you could see gravity, it wouldn't look like lines pulling downward but like ripples in still water. Each planet, each star, sends out waves of distortion, subtle undulations that travel through space-time. When massive objects collide, those waves become strong enough to be felt, like distant thunder. They pass through us constantly, changing the shape of the universe by a fraction of an atom, yet we never feel them. We live inside the music, unaware of the song. Even black holes, for all their darkness, are part of that melody. Their gravity doesn't destroy the pattern, it defines it. Around them, stars spiral in luminous arcs, gas clouds stretch into ribbons, light itself twists into circles of fire. The very structure of galaxies depends on their silent pull. In their stillness, they give the universe its rhythm. When you look at the night sky, every glimmer you see is a note played by gravity. Each star exists where curvature allows, balanced between falling and flying away. The Milky Way's spiral arms are frozen waves in that vast fabric, shaped by a gravity so immense and so patient that we can only perceive it across billions of years. Gravity's quiet voice has been speaking since time began, folding the newborn universe into order, shaping chaos into form. It asks for nothing, demands nothing, yet everything listens. Even light, the swiftest traveler, cannot ignore its call. And when light itself finally bends, when it curves around the unseen, we glimpse the depth of that silence, the steady, elegant whisper of a universe shaping itself. A star is a delicate balance between two opposing desires. Outward, the pressure of fusion pushes fiercely, powered by the endless dance of hydrogen into helium. Inward, gravity pulls with silent patience, trying to reclaim what was once scattered. For millions, even billions of years, these two forces hold each other in check. Light pours outward, gravity presses inward, and equilibrium gives the star its life. But nothing in the universe lasts forever. When the fuel runs low and fusion begins to falter, gravity senses its chance. It doesn't rage or strike. It simply waits, steady and certain, until the star can no longer resist. The collapse begins quietly, invisibly, at first. Deep in the core, temperatures soar as the last traces of fusion sputter and die. Without the outward pressure of new energy, the heart of the star starts to shrink. It falls in on itself, faster and faster, as if the entire star is inhaling. Layers of matter cascade inward, each pulled harder than the last. Protons and electrons, once kept apart by the strength of atomic forces, are crushed together, forming neutrons. The structure that defined matter begins to blur. The boundaries between what is and isn't an atom dissolve. If the star is small enough, it might find a new kind of balance, ending its life as a white dwarf or neutron star, dense but stable. But if it is massive, more than 3 times the mass of our sun, then even the neutrons cannot hold. There is no force left in the universe to resist the pull. Gravity wins completely. The collapse becomes unstoppable, exponential. Every fraction of a second, the core shrinks by half again, and again, and again, until the concept of smaller loses meaning. At that point, the equations of physics themselves begin to tremble. Space folds inward so sharply that distance ceases to exist. Time stretches until it frays. Density grows without bound. The star's entire mass, once spanning millions of kilometers, is now confined to a region smaller than an atom, smaller than anything that can be imagined. The fabric of reality pinches into a single perfect point. The singularity is born. It is not a thing in the traditional sense. It has no surface, no texture, no form that can be seen or touched. It is pure collapse. An idea of gravity so complete that geometry itself fails to describe it. The laws that govern matter, energy, and light all stop working here. Einstein's equations predict it, but they also warn us. Beyond this point, the mathematics end. It's as if the universe writes a sentence so complex that even it cannot finish. The death of the star is violent, but what follows is strangely calm. The outer layers are flung outward in a supernova, a final outburst so bright it can outshine entire galaxies. What remains behind is invisible. Not even light escapes the gravity of what's left. The space around it twists into a funnel with no bottom, and from that moment onward, the singularity hides behind its veil. The event horizon, its presence known only through what it devours. Yet in this destruction, something astonishing happens. The same process that ends a star's life seeds the universe with its future. The heavy elements, born in the explosion, iron, gold, carbon, scatter outward into space. They drift, cool, and one day become planets, oceans, living things. Every atom in your body once belonged to a star that collapsed and died. The singularity is both an ending and a beginning, a door that closes and opens at once. It's easy to think of the singularity as terrifying, a place of infinite density and no return, but it's also the universe's most profound act of transformation. Matter becomes geometry, energy becomes curvature. The star doesn't vanish, it changes its role. It stops shining and begins shaping. Its gravity will govern the motion of stars, the flow of gas, the rhythm of galaxies. If you could stand far enough away to see it all unfold, the collapse would appear almost gentle. The light would fade, the core would dim, and then there would be silence. But in that silence, something eternal begins. The singularity, invisible and absolute, hums softly beneath the surface of reality. A reminder that creation and destruction are never opposites, only stages of the same cosmic breath. If space could sing, a black hole would be its lowest note. Not the crash of something monstrous, but a sound so deep it hums beneath hearing. Long, patient, and endless. The universe speaks in gravity, not air, and where a black hole lives, the very fabric of space vibrates. It stretches and relaxes like a drumhead struck by invisible hands. When scientists say they've heard a black hole, what they mean is this: the silent ripples of space-time turned into frequencies we can feel, a translation of distortion into tone. Imagine a pair of black holes orbiting one another, locked in a dance billions of years old. They spiral closer, slower at first, then faster as gravity tightens its grip. Each revolution sends out a wave, a tremor, through space-time itself, propagating outward at the speed of light. Those waves are not made of sound, but when transformed into something the human ear can perceive, they become a rising note, a gentle hum that climbs and climbs until, in its final heartbeat, it merges into one drawn-out sigh. LIGO recorded such a sound in 2015, two black holes colliding a billion light-years away. In that faint chirp, less than a second long, humanity heard the universe's voice for the first time. That sound was not carried by air. It was carried by the warping of existence. Each crest of the wave stretched space itself, your body, the planet, the instruments that caught it, by less than the width of a proton, and yet that infinitesimal pulse carried the energy of 3 suns. The collision did not roar, it resonated. It was the sound of falling made eternal. If you could hover safely near a black hole, listening to the matter spiraling inward, you would not hear with your ears but with your bones. The gas and dust circling the event horizon form what's called an accretion disk, a ring of friction, heat, and velocity. As matter orbits, it rubs against itself, shearing into plasma, glowing in X-rays and gamma light. These waves can be converted into frequencies within human range, revealing a strange music of the void. The deeper the orbit, the higher the pitch, until at the inner edge of the disk, The tones bend and smear, distorted by gravitational redshift. It's as if sound itself slows down, stretched thin by proximity to oblivion. NASA once translated the data from a supermassive black hole at the center of the Perseus galaxy cluster into audible sound. The result was a deep, unsettling vibration, 58 octaves below middle C, too low for any instrument on Earth to play. To make it audible, scientists raised it by billions of times. What emerged was not a scream or a roar, but a cosmic moan, like wind dragging over the mouth of eternity. It is the oldest, lowest sound ever detected, reverberating through hot gas spread across hundreds of thousands of light years. The black hole plays its environment like an instrument, pulling sound from gravity and time. The accretion disk sings in chaotic harmonies. Magnetic fields twist through its plasma, like taut strings, snapping and reconnecting with bursts of radiation. Each flare releases a pulse, brief, bright, and sharp. If translated to sound, these pulses would resemble staccato notes overlaying a deep drone. Together, they would form a song both beautiful and terrifying, the rhythm of creation and destruction interwoven. It's a kind of lullaby written by physics itself. There are moments when the falling matter seems to waver, hesitating at the brink. Light scatters in spirals, sound deepens, and the motion of everything nearby sinks into a strange, unified beat. It's as if the black hole draws in not just matter, but rhythm. The frequency of falling matter, the pulse of bent light, the flutter of gravity waves, they align for a moment, then dissolve. No human ear can truly hear it, yet somehow the body understands. The sound of a black hole is not in the air but in the bones of reality, resonating with the same quiet that hums inside every atom of you. When we listen to those recordings, the sonified whispers of colliding stars, we are hearing time folding. Each note represents distances and durations we cannot comprehend, yet they reach us in the simplest way possible, as vibration. You can close your eyes and feel it, the universe breathing in and out, slow and deep. The sound of falling isn't chaos, it's gravity's melody, written in waves instead of words. The black hole doesn't destroy the music of the cosmos. It collects it, deepens it, slows it, until it becomes one perfect, continuous tone. Somewhere, far from where you are, a star is falling, and space itself hums in response. That hum will travel forever. It will never fade, only stretch. And if you were very still, very quiet, you might realize you've been hearing it all along. In April of 2019, humanity saw the unseeable. Across the world, telescopes linked together to form a single Earth-sized eye, peering deep into the heart of another galaxy, 55 million light-years away. What it revealed was not a photograph in the ordinary sense, but something closer to a mirror, one that reflected not light, but understanding. A dark circle surrounded by a glowing ring, soft and golden, like an eclipse captured in a dream. This was the first image of a black hole, or rather, the first glimpse of its absence. The black hole itself is invisible. No light escapes its gravity. No reflection returns. What we saw instead was the edge of that invisibility, the event horizon's silhouette cast against the bright fury of surrounding matter. The light we see in that ring has been twisted by gravity, bent into orbits that loop around the void again and again before finally escaping toward Earth. Every photon in that image has taken a tortuous path, curving through warped space, delayed by time itself. What you see is not the moment it happened, but an accumulation of moments, stitched together by the geometry of gravity. The Event Horizon Telescope was not a single instrument, but a collaboration of 8 observatories scattered across the globe, synchronized to the rhythm of atomic clocks. Together, they formed a network capable of resolving detail finer than any telescope could alone. It's a technique called very long baseline interferometry, a way of turning Earth into a lens the size of its diameter. Over several nights, these telescopes recorded radio waves from the galaxy M87, collecting petabytes of data too vast to transmit electronically. The information was stored on hard drives, flown by airplane to a central point, and combined. Only when the data from every corner of the planet were woven together did the image emerge. What appeared was almost mythical, a ring of fire, uneven in brightness, with one side glowing more fiercely than the other. That asymmetry is the result of motion, gas swirling around the black hole at nearly the speed of light. The side rotating toward us appears brighter because the light is compressed by relativistic effects, while the opposite side dims as it moves away. The ring isn't solid or still. It's a storm of radiation and plasma orbiting an abyss. The dark center, the shadow, isn't the black hole itself, but the point where light paths vanish forever. It's the outline of the unknowable, drawn by its own gravity. To call it a photograph is almost misleading. A camera captures reflected light from surfaces, frozen in an instant. This image captures the bending of space-time, an imprint of curvature itself. It's less a snapshot and more a map of warping, a visible echo of Einstein's equations. The bright ring you see could only exist in a universe shaped by relativity. Without the theory, the picture would make no sense. With it, the image becomes a confirmation, not of what black holes look like, but of how the universe behaves when pushed to its extremes. When scientists first processed the data and saw the ring appear on their screens, there was silence in the room. For years, it had been a concept, a simulation, a prediction in textbooks and code. And suddenly, there it was, proof that the equations of space-time had drawn something real in the cosmos. The ring's diameter matched what Einstein's mathematics had foretold almost exactly. 100 years after general relativity first predicted such objects, the universe had answered back. That dark circle in the middle, though, it's what captures the imagination. It isn't merely a void, it's the outline of time's end. The light we see around it circles a gravitational pit so deep that once crossed, even causality cannot escape. To look into that shadow is to look at the border between what can be known and what must remain hidden. It's not a hole in space, but a distortion of it, a place where geometry itself curves inward and never comes back. If you look closely, you'll notice that the image seems soft, almost hazy. That's not imperfection. It's truth. The light from the accretion disk blurs as it races around the event horizon, smeared by speed and gravity. What we see is not the chaos of motion, but the calm pattern it leaves behind. The shadow is constant, but the ring flickers, flares, and breathes. Even now, that black hole is still feeding, still shifting, its shape alive with the rhythm of falling stars. The picture changed how we see not just black holes, but ourselves. For the first time, humanity used its collective reach to look beyond the limits of light. We didn't photograph a thing. We captured a boundary, a threshold where the universe folds back upon itself. What shines in that image is not just plasma and radiation. It's geometry illuminated, a portrait of gravity drawn by light that almost didn't escape, a glimpse of a truth too vast to hold, hovering forever on the edge of night. There exists a place around a black hole where light forgets what it means to travel in a straight line. It neither escapes nor falls. Instead, it circles endlessly, caught in a perfect loop, a fragile ballet of photons orbiting on the knife edge between freedom and oblivion. This is the photon sphere, a glowing ring of possibility where the universe bends so sharply that light itself becomes captive to its own momentum. Imagine a beam of light passing near a massive object. Far away, it travels straight, unbent, and unwavering. But as it approaches a black hole, the fabric of space-time curves around the immense gravity, and the light bends with it. The closer it gets, the stronger the deflection becomes. At just the right distance, 1.5 times the radius of the event horizon for a non-rotating black hole, the bending becomes complete. A photon launched tangentially at that distance will circle the black hole indefinitely, tracing a perfect orbit around the void. Any closer, and it spirals inward, swallowed forever. Any farther, and it escapes, though distorted and delayed. The photon sphere is that exact in-between, the border where light hesitates. But this balance is exquisitely fragile. The orbit is unstable, like a marble balanced on the peak of a hill. The smallest disturbance, a fluctuation in energy, a ripple in gravity, a stray particle sends the photon drifting inward, or outward, ending its eternal loop. Light in the photon sphere does not remain forever. It lingers. It whirls for a few turns, maybe dozens, before escaping or falling, its path curved into graceful spirals that fade into shadow or burst outward in a final flash. To us, from afar, these escaping photons form the glowing edge of the black hole's shadow. What we perceive as the bright ring in the first black hole image is in part light that has circled multiple times before reaching us. The photon sphere draws the boundary between what is seen and what is lost. If you could somehow stand near this region, not on a surface, for there is none, but in free fall beside it, the sky would warp into impossible shapes. You would see the black hole's shadow directly ahead, but also behind and above you, reflected and refracted by gravity. Light from the universe would curve and wrap, duplicating stars, bending galaxies into rings of color. Every direction would lead back to the black hole's outline, a cosmic mirage created by space-time folding upon itself. It would be like floating inside a lens that has forgotten which side is front. The photon sphere reveals something profound about the nature of gravity, that it doesn't simply pull objects in, it shapes the very geometry of vision. It decides what can be seen and from where. It is gravity's most elegant illusion, painting the edges of reality with light that almost didn't escape. And because black holes can spin, their photon spheres twist as well, stretched into whirling ovals where space drags along with rotation. In these regions, light orbits, not only because of gravity's pull, but because space-time itself is being carried around, twisted like a whirlpool. Some photons race with the spin, surviving longer. Others fight against it and are soon consumed. The dance becomes asymmetric, a spiral of light tugged by the rotation of the universe itself. What makes the photon sphere haunting is that it exists, entirely in theory, and yet leaves its fingerprints everywhere. We cannot see the photons that linger there directly, but we see their echoes, the distorted glow, the gravitational lensing, the shimmering edge of the shadow. It's a boundary that isn't physical, yet still paints the cosmos with its presence. In its fragile orbits lies the poetry of balance, a world where motion is endless but stability is impossible. Every photon caught in that ring carries with it a story of near escape. Each one could have fallen inward, lost forever, yet somehow it found the one narrow path that curved just right to circle again and again before slipping free. What we see from Earth is the collective light of these brief survivors, the radiation that has skimmed the edge of eternity and returned, whispering what it saw before vanishing into the night. The photon sphere is where light learns humility. It reminds us that even something as constant as a beam can be bent, delayed, and held captive by gravity's persuasion. It's the quiet theater where motion meets stillness, where light becomes a mirror for the curvature of existence itself. It doesn't shine by its own power, but by its surrender to the geometry that guides it. And in that surrender, it becomes beautiful. Falling toward a black hole is not a plunge, but a stretching of time and self. At first, you would feel nothing unusual. The pull of gravity would seem steady, even gentle, as the black hole loomed ahead, a dark sphere rimmed with dim fire. But the closer you came, the more gravity would begin to change its mind about you. The side of your body nearest the black hole would feel a stronger tug than the far side. Your head and your feet would begin to live in different gravitational worlds. You would not notice it all at once. It would begin as a pressure, a strange lengthening, as though space were softly pulling you apart. This is the beginning of spaghettification. The name sounds whimsical, but the reality is exquisite and terrible. Gravity stretches you vertically while squeezing you horizontally, turning your body into a narrow thread of atoms drawn toward the singularity. The nearer you fall, the greater the difference in gravity between your top and bottom, between one heartbeat and the next. The pull increases by unimaginable factors every second, until no molecular bond can resist. Even the nuclei of atoms begin to feel it, their orbits torn into ribbons of charged fragments spiraling downward. You don't fall in all at once. You fall piece by piece, every fragment following its own doomed trajectory. Yet if someone were watching you from far away, they would never see you reach the end. To them, your descent would slow until you appeared frozen above the event horizon, your light stretched redder and dimmer with every passing moment. You would fade into a deep crimson, then to black, suspended in time, your image lingering like a ghost just above the edge. From their view, your fall never completes. You become a memory painted on the surface of the horizon. But from your own perspective, you continue falling smoothly, inexorably, through the point of no return. Time itself flows differently for you now. Your seconds are their eternities. The paradox is beautiful. Two truths coexist. To the outside world, you never arrive. To yourself, you fall without hesitation. The universe allows both versions to be real. It's a reminder that time is not universal but curved, stretched by gravity just as surely as your body is. What looks eternal from one angle can be fleeting from another. To watch someone fall into a black hole is to see time and matter unravel together, each surrendering to the same geometry. The physics of spaghettification is relentless, but strangely precise. Near a small black hole, the tidal forces are so extreme that you would be torn apart long before crossing the horizon. But near a supermassive black hole, like the ones at galactic centers, the transition would be deceptively calm. The horizon there is vast, and the gradient of gravity more gradual. You might pass through without immediate harm, drifting into darkness as the light of the universe bends around you. Only deep inside, where the curvature becomes absolute, would the stretching reach its final, silent crescendo. In that moment, your atoms would elongate into streams of energy, drawn into the singularity where space and time cease to exist separately. There is no longer a distinction between motion and being. You become part of the black hole's mass, your energy folded into its gravity, your history compressed into a point smaller than imagination allows. From the outside, this act of absorption never ends. The last flickers of your light hover forever on the edge, encoded into the surface of the horizon, waiting for a moment that never comes. The process is violent in concept, yet tranquil in experience. You never feel yourself torn apart, because you stops meaning what it once did. Every particle that made you begins to experience its own time, its own fall. Identity dissolves into motion. From the inside, there is no pain, only surrender, an endless reaching that never touches bottom. The universe does not break you, it redefines you. To fall into a black hole is to learn what it means to lose not just place, but perspective. To see yourself stretched across space and time, one version frozen at the edge, another spiraling inward beyond rescue. It's destruction, yes, but also transformation. The rearrangement of matter into meaning, of experience into geometry. The spaghettification of form mirrors the elongation of time, until both become infinite threads drawn toward the same vanishing point. And somewhere, at that final convergence, all that you were, every breath, Every heartbeat, every flicker of thought becomes part of the black hole's quiet gravity. Your fall is complete, but it never ends. For a long time, black holes were thought to be the ultimate prisons, places where everything ended and nothing escaped. Even light, the swiftest traveler in the universe, could not outrun their gravity. They were absolute, the final punctuation marks of existence. But then, Stephen Hawking listened closely to the silence and heard something faint within it, a whisper, almost imperceptible, at the edge of nothing. It was the sound of the impossible. Black holes were not perfectly black. They glowed. They breathed. The idea was born not from astronomy but from mathematics, from the uneasy conversation between two of physics' greatest languages. One spoke in the smooth curves of Einstein's relativity, describing gravity as geometry. The other stuttered in probabilities, quantum mechanics' language of uncertainty and flicker. These two theories seldom agree, but Hawking brought them face to face at the edge of the event horizon, where both must be true at once. What he found there was astonishing. Even the vacuum of space, it turns out, is not empty. It teems with momentary pairs of particles that appear and vanish, flickering into existence before canceling each other out. They are born from the quantum uncertainty of energy itself, always in pairs, one particle, one antiparticle. Normally, these twins meet again almost instantly, annihilating in a burst that returns their borrowed energy to the void. But near the horizon of a black hole, the rules change. Gravity tilts the playing field. When one of these pairs forms right at the edge, sometimes gravity pulls one particle inward while the other escapes. To an observer far away, that lone survivor looks like radiation emanating from the black hole. Energy has been released, however faintly, and the black hole's mass decreases in return. It is as though the black hole has exhaled. The energy comes not from nothing, but from the black hole itself, traded away to preserve the balance of nature. Over eons, this slow breathing continues until the black hole grows smaller, dimmer, and finally evaporates completely. This gentle leakage of energy is called Hawking radiation. It is unimaginably weak, so faint that for any black hole we know, the glow is drowned out by the background hum of the universe itself. Yet its implications are enormous. It means black holes are not eternal. They can die. They fade not in explosion, but in a sigh so long and quiet it outlasts galaxies. A black hole born from a collapsing star might endure for trillions of years, but even it cannot escape the arithmetic of evaporation. Hawking's whisper challenges our understanding of reality itself. If black holes evaporate, what happens to the information they once contained? Every bit of matter that falls in carries structure, quantum patterns, histories, identities. The universe, according to quantum law, does not forget. But when a black hole dissolves into radiation, that structure appears lost, reduced to featureless heat. It's as if the universe has deleted its own memory. Hawking called this the information paradox, and it remains one of the deepest mysteries in physics. Some theories suggest the information is encoded in the radiation, hidden in correlations too subtle to decode. Others propose that it clings to the event horizon, like writing on a boundary that can never be read directly. The paradox is unsolved, but the whisper persists. It reminds us that even in the darkest corners of creation, the universe keeps communicating, faintly but continuously. Black holes are not silent tombs, but participants in the grand conversation between energy and entropy, between geometry and uncertainty. Each particle that escapes from their edges is a message, a flicker of balance asserting itself against the weight of gravity. When Hawking described this radiation, he changed the black hole from a devourer into something more complex, a dying star's last, slow music. He showed that even the most absolute boundaries leak, that even the deepest silence holds a pulse. The discovery was a reminder that nature never allows perfection. Every wall, no matter how strong, hums with imperfection. Every abyss breathes. If you could stand near a black hole and listen, not with ears, but with understanding, you would not hear thunder or roar. You would hear the softest murmur, the thermal whisper of creation giving some of itself back. It would be the sound of time unspooling atom by atom, of a star's memory slowly fading into warmth. And perhaps that's the lesson buried in the whisper Hawking found, that even in loss there is exchange, that even in endings there is conversation. The black hole's voice is faint, yes, but not gone. It speaks in photons and patience, in quantum flickers at the edge of darkness. The universe, it turns out, never stops talking. It just lowers its voice. When something falls into a black hole, it seems to vanish. Matter crosses the horizon and disappears from view, its light stretched and faded until it slips beneath that invisible boundary. To an observer outside, it's as if the universe has deleted a page from its own story. A star, a planet, even a photon, gone, erased, leaving behind only the trembling ring of the black hole's gravity. But the universe, according to its own deepest laws, doesn't do erasure. Quantum mechanics insists that information, the precise details of every particle's identity and arrangement, can never truly vanish. Energy can change form, matter can be rearranged, but the underlying pattern must persist. And so begins one of the strangest puzzles in physics, the black hole information paradox. When Stephen Hawking first proposed that black holes emit radiation, it came with an unexpected cost. Hawking radiation, as it's called, carries no imprint of what fell in. It's pure, random heat, featureless and indifferent, like the dying hiss of static from a burned tape. Over unimaginable stretches of time, as the black hole radiates away its mass, it shrinks and finally evaporates. If that radiation is truly random, then the information inside is lost forever. The particles, their histories, the quantum states that define them, all gone. But that's not supposed to happen. The universe's equations demand consistency. Information cannot simply cease to exist. Yet relativity and quantum mechanics, when forced together at the edge of a black hole, seem to disagree. To grasp the paradox, imagine throwing a book into a fire. The pages burn, the ink blackens, and the words crumble into ash and smoke. But the information, the precise arrangement of molecules, the structure of each letter, still lingers in the patterns of heat, light, and gases released. In principle, with perfect knowledge of every particle, one could reconstruct the story. Nothing is truly lost. It's only scrambled. A black hole seems to defy that rule. When it evaporates, it leaves behind only heat, no code, no trace. It's as though the universe burned the book and forgot the language it was written in. Some physicists refused to believe that could be true. They began to look for where the information might hide. One idea suggests that the information never crosses the horizon at all. Instead, it becomes imprinted on the surface, encoded in subtle quantum ripples known as the holographic principle. In this view, the black hole's surface is like a cosmic hard drive, recording everything that falls in as a two-dimensional pattern, a shimmering memory projected across its edge. The inside, the darkness, is just a geometric illusion. The true story is written on the boundary, where space and time trade places. It means that every secret a black hole swallows is preserved, not destroyed, etched in faint mathematical fire along its rim. Another possibility is that the information escapes with the radiation itself. Perhaps Hawking's calculations, though, brilliant, missed a whisper of correlation, a hidden order within the chaos. In that case, the black hole's evaporation would not erase information, but release it slowly, bit by bit, disguised in randomness. The universe would not lose its memory. It would merely speak it back in a dialect too subtle to decode. Each photon of Hawking radiation would carry a fragment of truth, a microscopic echo of what once fell inward. But there are more unsettling ideas. Some theories suggest that information might remain trapped at the horizon, stored in quantum entanglement across the boundary. Others propose that the black hole's end is not quiet evaporation, but a transition, a bridge to another universe, where the information continues in a different form. Each solution bends the rules of physics just enough to keep the others from breaking. The paradox remains a mirror in which our understanding of reality reflects its limits. At the heart of it lies a simple, almost poetic question: does the universe forget? Every theory, every equation, every model seems to resist that idea. From the faintest particle to the collapse of galaxies, nature keeps its ledgers balanced. The black hole, with its event horizon and its fire of radiation, stands at the edge of that accounting, testing whether the cosmos is as precise as it claims. If information truly vanishes, then something profound must give way. The laws of quantum mechanics, the symmetry of time, perhaps even the fabric of causality itself. But if it remains, encoded in the black hole's fading light, then black holes are not graveyards but archives, keepers of everything they consume, storing it in patterns we cannot yet read. The fire that seemed to destroy might instead preserve. When a black hole finally dies, evaporating into a final whisper of radiation, the information paradox reaches its quiet conclusion. Either the universe has kept every secret, hidden in the ash, or it has allowed one mystery to slip away. Perhaps both are true. Perhaps forgetting and remembering are not opposites at all, but two sides of the same horizon. The fire burns, the code shimmers, and somewhere in the dark, the universe writes its own name over and over again, never losing the words, only changing the way they're told. The idea began as a question whispered into the silence of theory. What if a black hole isn't an end at all? What if the collapse that seems to erase the universe instead opens it? An unseen passage between distant places, or even between entirely separate realities? In Einstein's equations, space and time are flexible, curving and folding under the weight of mass and energy. And if they can bend, perhaps they can fold so tightly that two distant points touch, like paper pressed together. That fold, if it exists, would be a wormhole, a bridge through space-time, a tunnel between wheres and whens. In the math, wormholes are allowed. They fall out of general relativity like a secret clause in the laws of gravity, an unexpected door written into the structure of reality itself. The equations describing black holes can be extended to describe something else entirely. Two universes, connected by a narrow throat, a passage surrounded by unimaginable density. To cross it would be to step outside everything you know, to travel not through space, but through geometry. The wormhole is not built of matter or light, but of pure curvature, the universe folding in on itself, and then, impossibly, opening again. Some versions of the theory suggest that every black hole might have a twin, a white hole, on the other side. Where a black hole swallows everything, a white hole would eject it, expelling matter and energy instead of devouring them. It would be the mirror opposite of destruction, a cosmic exhalation. In this vision, the singularity becomes a pivot, a hinge between two realms. Matter collapses through the black hole and reappears elsewhere, reborn in a burst of light and motion. The universe might be full of such hidden doorways, black and white holes linked in pairs, each consuming and releasing in balance. But no one knows if such a thing could survive reality's turbulence. Wormholes, by their very nature, are fragile. According to the equations, an unprotected wormhole would collapse faster than light could cross it. The tunnel pinches shut almost instantly under the crushing pressure of its own gravity. To keep it open, something extraordinary would be required. A matter with negative energy, a substance that doesn't exist in any ordinary form. This exotic matter would repel rather than attract, pushing space-time apart instead of drawing it together. Theoretically, it could hold the throat of a wormhole open, stabilizing the passage long enough for something, or someone, to pass through. The idea sounds impossible, but then so did black holes themselves before we saw their shadows burn across the sky. Scientists have tried to imagine what it would mean to travel through such a bridge. You would not move faster than light. Instead, you would take a shortcut through the structure of reality. A journey across galaxies might take only moments, the far edges of the universe connected by an invisible corridor. From the outside, you would seem to disappear into the mouth of a black hole and never emerge. But inside the geometry, time and distance would bend differently. The fall could end not in annihilation, but in arrival. And then there are the wilder dreams, that wormholes could connect not just regions of space, but different times entirely. That the universe might allow backward travel, if only for the briefest, most impossible instant. If true, it would mean that black holes do not just curve space, they curve causality itself, creating knots in the thread of time. Some physicists argue this would violate too many principles. That paradox would tear the structure apart. But the equations do not forbid it outright. They simply whisper that, under the right conditions, time might fold back on itself and peek through the seam. Even if wormholes can't exist in any physical sense, they persist in our imaginations because they represent something deeply human, the refusal to accept finality. To call a black hole a door instead of a tomb is to assert that nothing, not even gravity, can extinguish curiosity. Every generation of physicists returns to the same thought. What if there's more beyond the fall? What if the universe, in its endless complexity, refuses to end in silence? Maybe wormholes aren't real tunnels, but metaphors written into the mathematics, hints of how incomplete our understanding still is. Or maybe they exist, flickering open and shut on quantum scales too small to see. Tiny bridges connecting regions of space-time like neural links in the brain of the cosmos. If we could listen closely enough, perhaps we would hear them, soft distortions, whispers of escape. The truth, as always, rests somewhere between myth and math. The wormhole remains both a promise and a warning, a structure made of possibility. Whether or not it ever opens for us, it tells us something vital about the universe we inhabit. That even where everything appears to end, equations leave room for a path forward. That the geometry of existence, no matter how dark or curved, still allows the shape of hope. When a black hole spins, it changes the shape of everything around it. The simple, perfect collapse that defines a non-rotating black hole becomes something more complex, more alive. Gravity is no longer just a pull downward. It becomes a twist, a rotation so powerful it drags space itself into motion. This phenomenon, called frame dragging, means that near a spinning black hole, even light cannot stand still. Everything, even the concept of stillness, is caught in the whirl. In the heart of such a black hole, the singularity is no longer a point. Spin stretches it into a ring, a thin loop of infinite density, rotating at the limit of possibility. This ring's singularity doesn't just curve space, it tears and folds it into forms that defy intuition. Around it, time and space exchange roles, looping and spiraling in ways that break the boundaries of cause and effect. The black hole becomes a vortex of geometry, where every direction eventually leads inward, yet somehow never arrives. The Kerr black hole, as it's known, carries angular momentum, the cosmic memory of its creation. When the star that birthed it collapsed, not all of its motion vanished. The leftover spin survived, magnified by gravity's compression, until the entire structure of space-time began to rotate. The faster the spin, the more extreme the warping becomes. Near the poles, the horizon remains close, but around the equator, it stretches outward, flattening the once spherical event horizon into an oblate shape. Beneath that horizon lies a second one, a hidden boundary called the inner horizon, where gravity's pull reverses direction. Between these layers, physics dances on the edge of contradiction. Inside this region, something extraordinary happens. Instead of falling toward an inevitable end, a traveler might find themselves drawn into a tunnel of warped space-time. The equations suggest that the ring singularity could act as a gateway, not to another universe, but to another region of our own, a distant corner of reality connected by the strange rotation of gravity. Passing through it, though, would mean entering a domain where time behaves like space and space behaves like time. You wouldn't move forward anymore. You would move deeper into moments, walking through seconds as though they were corridors. The ring singularity is not just a mathematical trick. It's the universe's most elaborate knot. Around it, space-time is twisted so violently that closed time-like curves appear, paths that loop back on themselves, allowing a traveler, in theory, to return to their own past. The black hole becomes a machine that doesn't run on gears or engines but on geometry. The laws that forbid paradox begin to tremble here, unsure of themselves. In the equations, nothing stops you from circling back to the instant you began, though the universe may have its own ways of preventing such journeys from ever being real. If you could look upon the ring singularity, though no human eye ever could, you might see not darkness, but distortion. Every photon, every piece of light that grazes it, is twisted into spirals, dragged around the vortex before being flung away or consumed. The singularity is infinitely small, yet vast in influence, defining the structure of everything nearby. Its spin gives rise to an ergosphere, a region outside the event horizon where nothing can remain motionless. Within this zone, energy can be stolen from the black hole's rotation, a kind of cosmic loophole in the law of conservation. Even gravity has seams, and spin finds them. The thought of a ring instead of a point changes the poetry of the black hole entirely. A point is final, one coordinate, one destiny. A ring is continuous. It has direction, rhythm, return. It suggests that even within collapse, there is motion, a kind of persistence that refuses to stop. The singularity doesn't merely destroy. It spins, it remembers, it rewrites the rules in the language of rotation. The Kerr black hole becomes less a grave and more a whirlpool, endlessly swallowing and stirring the universe into new configurations. There's a strange comfort in the idea that spin could soften infinity, that motion itself could reshape the void. It reminds us that nothing in nature stands still. Not stars, not space, not even the end of time. The ring singularity is proof that the universe doesn't collapse quietly. It dances as it dies. Inside that dance, within the infinite curvature and impossible loops, lies the echo of every rotation the cosmos has ever known. The black hole spins, and through that spin, it whispers a truth older than stars, that even in the deepest gravity, the universe cannot stop moving. If black holes are the universe's mouths, endlessly swallowing, then white holes are its mirrors, regions that can only exhale, never breathe in. They are the perfect opposites, mathematical twins, born from the same equations that describe collapse but played backward in time. Where a black hole drags everything inward, a white hole hurls everything outward. No matter, no light, no information can cross its threshold from the outside. It doesn't devour, it rejects. It's a gate that opens only one way, into the past rather than the future. White holes emerged first, not from observation, but from the logic of Einstein's general relativity. If space-time could fold so completely that nothing could escape, the equations also allowed the reverse, a fold so strange that nothing could enter. In the simplest mathematical extensions of a black hole's geometry, the singularity doesn't sit at the end of time but on the other side of it. Beyond the black hole's horizon lies a mirror domain, where gravity's direction flips and the arrow of time runs in reverse. For every act of collapse, there exists a corresponding act of expulsion. The math insists that both are possible. Reality, however, is less certain. In the language of equations, white holes seem inevitable, yet none has ever been seen. Their existence would require initial conditions so perfect so improbably precise that the universe itself would have to be engineered for symmetry. Even the smallest disturbance, a dust grain, a photon, a whisper of gravity, would be enough to destroy them. To remain pure, a white hole must remain perfectly sealed, untouched by time's entropy. It's a creature that cannot survive contact with the world, and yet the concept endures. Some theorists wonder if white holes might be connected to black holes through hidden tunnels of space-time, the other ends of wormholes, the cosmic outbreaths balancing the universe's constant inhalations. In this picture, every black hole could be paired with a white hole elsewhere, joined by an Einstein-Rosen bridge, where whatever falls into one emerges from the other. Matter collapses in one universe and explodes into being in another, energy reborn instead of erased. The black hole and the white hole would form a single continuous object, a cosmic hourglass in which time flows one way in the upper chamber and backward in the lower. Others imagine them not as existing now but as memories from the universe's beginning. The Big Bang itself, they suggest, might have been a white hole, a singularity not of collapse but of creation, spitting out energy and matter instead of swallowing it. In that sense, every atom, every photon, every breath of air could be the residue of a white hole's release. We may be living inside its echo, the light still spreading from its ancient eruption. If black holes are the ultimate absorbers of order, white holes are its defenders. They represent the universe's instinct to balance extremes, to keep the sum of its stories consistent. A black hole hides information behind an event horizon. A white hole exposes it, broadcasting energy into the cosmos with no explanation for where it came from. In one direction, time folds inward. In the other, it bursts outward in defiance. One is the silence after an ending, the other the noise of a beginning. Of course, it's possible white holes are only artifacts of mathematics, a kind of reflection produced when the equations stare too long at themselves. Physics often writes poetry it cannot yet prove. The formulas allow beauty that the universe might never perform. But sometimes, impossibilities in math have a way of finding their stage. Once, black holes were dismissed as absurd. Now we have seen their shadows glowing in the darkness. Perhaps white holes wait still, hidden not in the voids between stars but in the deeper folds of time where beginnings and endings blur. There's a haunting symmetry in the idea that for every collapse there might be an equal expansion, that nothing is ever fully lost, only transformed through inversion. Black holes are endings that pretend to be final, but if white holes exist, then every end is also a start written backward. The cosmos might not be a single narrative flowing in one direction, but a dialogue, gravity, and time speaking to one another in mirrored tones. And so we are left with the thought that somewhere, unseen, the universe may still be exhaling what it once inhaled, light spilling from hidden mouths of creation, echoes of stars that never fell, equations whispering to themselves about symmetry, about balance, about the possibility that even in the deepest darkness, there might exist a reflection that refuses to let anything truly stay gone. If you could keep shrinking, past molecules, past atoms, past the nucleus itself, there would come a point where shrinking no longer makes sense. A scale so small that even the word small loses meaning. This is the Planck length, about 100 million trillion times smaller than a proton. It is the boundary where space and time, once smooth and continuous, begin to flicker. Here, reality itself is not calm or solid. It seethes. It froths like the surface of boiling water. This is the quantum foam, the restless foundation beneath existence. Einstein imagined space-time as a fabric, flexible but smooth, curving gently around mass and energy. Quantum mechanics disagrees. It insists that nothing is ever truly still. Even in perfect vacuum, particles and fields quiver with uncertainty. The closer you look, the more chaotic they become. The Planck scale is where these two visions collide. The serene geometry of relativity, meeting the jittering probability of the quantum world. Gravity becomes unpredictable. Distances blur. The very idea of where and when loses its precision. At this scale, the vacuum is not empty, but alive. Virtual particles flash into existence and vanish again in unimaginably brief moments, borrowing energy from the void and returning it before time can object. The same process that gives rise to Hawking radiation near a black hole's edge plays out everywhere, all the time, in miniature. Every cubic centimeter of space contains this hidden storm, a dance of ephemeral particles and warped geometry. Even nothingness has texture. Physicists describe it as foam, because space-time may resemble a shifting network of tiny bubbles, constantly forming and collapsing. Each bubble represents a transient curvature, a microscopic fluctuation in gravity itself. Imagine space not as a blank canvas, but as a living surface, folding and unfolding with every heartbeat of the universe. From far away, these tremors average out, giving the illusion of stability. But up close, it's chaos. Valleys and peaks in the very metric of existence, ceaseless and unpredictable. The singularity inside a black hole may not be a true point of infinite density at all, but a symptom of the limits of our understanding. When gravity compresses matter beyond all known scales, the smoothness of space-time breaks down into quantum foam. Instead of an infinitesimal core, there may be a region of wild fluctuation, a storm of geometry so intense that our current laws collapse. The singularity could dissolve into this quantum sea, replaced by uncertainty rather than infinity. In this way, black holes may not destroy the laws of physics. They may reveal where those laws change their language. The Planck scale is so remote from human experience that it defies imagination. If an atom were enlarged to the size of the solar system, the Planck length would still be smaller than a grain of dust within it. Yet everything we see, the galaxies, the stars, the air, emerges from these trembling depths. The foam beneath reality is the quiet architect of structure. It's where gravity and quantum mechanics meet in uneasy conversation, negotiating the terms of existence. Some theories suggest that space-time itself might be quantized, made of discrete units, like the pixels of a cosmic screen. Loop quantum gravity envisions the universe woven from loops of energy, their intersections forming the scaffolding of space. In this view, what we call emptiness is built from threads of vibration, tiny knots that give rise to distance, direction, and time. Others propose that strings, one-dimensional filaments vibrating in multiple dimensions, compose everything, including the geometry we move through. In both ideas, the foam is not chaos but code, the raw computation from which the universe is rendered. If we could somehow perceive it, quantum foam would not look like light or color but movement itself, the shimmer of being before form emerges. It would sound less like noise and more like a pulse, an endless murmur beneath all things. This is the hum that underlies gravity, matter, and thought. The same storm that roils inside a black hole also stirs between your atoms, an omnipresent tremor that connects the vast and the minuscule. Perhaps the most profound realization is that the universe is not built on solidity, but on fluctuation. What we think of as stable, space, time, even identity, is a calm surface resting on turbulent depth. The cosmos is not a monument, but a motion, every particle and every field arising from the foam and returning to it. What seems eternal is only what has, for the moment, found balance amid the storm. If singularities truly dissolve into this sea of uncertainty, then the universe contains no true edges, only gradients of order, fading into the quantum churn beneath. The foundation of everything is not fixed, but alive. The closer we look, the less we find structure, and the more we find movement. Beneath every galaxy and every black hole, beneath every breath, space-time trembles, whispering the same truth over and over, that even nothing is never still. Around every black hole, there is motion, furious, radiant motion. Long before the horizon, before light gives up its fight to escape, matter gathers in orbit, pulled into a whirl of impossible speed. This is the accretion disk, a vast and glowing ring of gas and dust spiraling toward oblivion. To fall toward a black hole is not to fall silently, it is to ignite. The friction of atoms, the crush of magnetic fields, the fury of gravity turning matter into energy, all of it creates a spectacle so bright that entire galaxies bow to its glow. This is the black hole's heartbeat, the pulse of creation thrumming at the edge of destruction. In that swirling disk, particles collide at nearly the speed of light. Temperatures soar to millions of degrees. The inner regions glow with X-rays, while the outer ones shimmer with visible light, radio waves, and gamma bursts. It's a paradoxical beauty, born from chaos. The same gravity that swallows everything also orchestrates this dance, shaping order from the ruin it creates. The disk becomes a living organism of physics, a self-sustaining storm, where gravity, magnetism, and radiation weave together in relentless rhythm. Every flicker of light, every burst of heat, is a heartbeat in the black hole's hidden body. Magnetic fields twist through the disk like invisible serpents, threading the plasma and winding tighter as they approach the center. They bend space and guide energy, funneling it upward into narrow jets that shoot from the black hole's poles. These jets can stretch for thousands of light years, cutting through interstellar darkness with precision. Each one is a cosmic lighthouse, shining with the brilliance of 1 trillion suns. When we look across the universe and see quasars and blazars, those distant, blazing points of light, they are not stars. They are black holes feeding, spinning, and breathing out columns of fire into the void. The jets form from what the black hole refuses to take. Not everything that falls toward the horizon crosses it. Some of the material, caught in magnetic turbulence, is redirected, accelerated outward at relativistic speeds. The black hole devours and rejects at once, consuming matter while hurling energy into the cosmos. It is both predator and creator. The same process that drives destruction fuels the birth of new stars as the expelled material seeds distant clouds of gas. The black hole's hunger, in its way, keeps the galaxy alive. To watch a quasar is to witness balance on a scale that defies comprehension. The inward pull of gravity meets the outward push of radiation in a near-perfect equilibrium. The energy output is staggering. Some quasars outshine entire galaxies, visible across billions of years. Yet behind that brilliance lies the ultimate silence, a singularity hidden beneath light so fierce that it erases its own shadow. The heart of the black hole beats in this paradox, rhythm and stillness bound together in perpetual tension. Scientists studying these accretion disks sometimes describe them in musical terms. The fluctuations in their brightness follow patterns like chords, oscillations like drum beats. X-ray emissions pulse and fade, tracing the orbits of gas as it spirals inward. Some black holes flicker in regular intervals, as if breathing in deep cosmic time. It's not metaphor. It's physics, a feedback loop between gravity, magnetism, and light that produces literal rhythm. A black hole's heartbeat can last seconds, hours, or even centuries, depending on its mass. The universe itself seems to hum in response, a background harmony that travels through the fabric of space. And yet, for all its violence, there's an elegance to the way a black hole feeds. Every movement follows the rules of energy and curvature. Nothing wasted, nothing truly chaotic. The jets that pierce space are guided by geometry, their alignment dictated by spin. Even the brightest eruptions obey an order written in the mathematics of relativity. From a distance, it looks like madness. Up close, it's a kind of grace, the calm precision of nature, doing what it must to remain whole. If we could translate this motion into sound, it might resemble the slow, low thrum of a drum beneath everything else, a cosmic metronome keeping time across billions of years. The black hole's heartbeat does not fade. It resonates through the fabric of the universe, echoing in the radiation we detect, in the galaxies it shapes, in the quiet laws that hold the stars in place. It reminds us that even in the deepest darkness, energy circulates, light escapes, and rhythm endures. At the center of chaos, there is order. At the heart of collapse, there is pulse. Every quasar, every blazar, every jet of light streaming through space is proof that destruction and creation are not opposites, but phases of the same breath. The black hole consumes and radiates, devours and illuminates, inhales and exhales across eternity. Its heartbeat is the sound of gravity, remembering that even darkness can burn. At the center of nearly every galaxy, including our own, there waits a single point of unimaginable gravity, a supermassive black hole. It sits there in near-perfect silence, invisible yet in control, as if the entire galaxy were built around its stillness. These titanic singularities, millions or even billions of times the mass of the sun, are the quiet architects of the cosmos. From their invisible thrones, they shape the structure, rhythm, and destiny of galaxies that stretch for hundreds of thousands of light years. For a long time, astronomers believed black holes were merely the aftermath of dying stars, cosmic graves, not governing forces. But as our instruments sharpened and our gaze deepened, something extraordinary became clear. The mass of a galaxy's central black hole is intricately linked to the mass of the stars around it. The bigger the black hole, the bigger the galaxy. Somehow, a region smaller than our solar system holds sway over billions of suns. It's as though gravity found a way to design, not just to destroy. When galaxies are young, their cores blaze with furious light. Gas and dust fall toward the central black hole, heating and spinning into brilliant disks that outshine everything around them. These are quasars, galactic hearts in overdrive, devouring and radiating in equal measure. The energy pouring from their centers can surpass that of every star in the galaxy combined. This radiation doesn't just escape into space. It pushes back on the very gas that feeds it, shaping how the galaxy grows. Too much light, and the gas that could have formed new stars is blown away. Too little, and the galaxy collapses under its own density. The black hole finds balance, guiding creation by restraint. In this way, black holes are both engines and regulators. Their outbursts send winds of charged particles sweeping through interstellar clouds, compressing some regions while dispersing others. From this invisible choreography, galaxies find their structure, spirals, ellipses, or the dense, spherical cores of ancient systems. Every burst of energy, every pulse of radiation, becomes a sculpting tool in the hands of gravity. Even silence plays a role. When the black hole rests, the galaxy breathes and grows. When it awakens, the galaxy stabilizes, reminded of its boundaries. The feedback between a supermassive black hole and its galaxy is one of the most delicate relationships in the universe. It's not domination, but dialogue. The stars feed the black hole with their deaths, and in return, the black hole feeds the stars by shaping the medium from which they form. It is a loop written into the very structure of space, an eternal conversation between collapse and creation. Without this balance, galaxies might never have formed the way they did. The universe could have been either too chaotic or too barren for light to organize itself into spirals and systems. Our own Milky Way has such a center, Sagittarius A*, a black hole 4 million times the mass of the Sunday. It sleeps now, quiet and unthreatening, but the scars of its past awakenings are written across the galaxy. Clouds of gas near the core still glow from ancient outbursts. Streams of hot plasma hint at the times it fed more greedily. Even in its dormancy, it anchors everything, holding the stars in their collective orbit, keeping the vast disk of the Milky Way from unraveling. If it were to vanish, our galaxy would not be torn apart immediately, but over eons, its order would dissolve. Gravity would drift into chaos, the stars losing their shared rhythm, the spiral arms fading into aimless motion. It's a strange kind of creation, the kind that works backward, building through destruction, stabilizing through hunger. A supermassive black hole does not assemble galaxies like an architect laying stones. It sculpts them the way a storm sculpts a coastline, eroding here, depositing there, its touch both violent and precise. From chaos, coherence. From gravity, grace. And yet, despite all that power, these galactic hearts are not tyrants. They are more like anchors, points of gravity that remind the universe where its center is. Every star that burns, every planet that spins, does so in the faint shadow of that central presence. The black hole does not command light. It defines the space in which light can exist. It sets the stage for everything else to unfold. When you look up at the night sky and see the soft band of the Milky Way stretching from horizon to horizon, what you're really seeing is the consequence of a single, silent force, an invisible mass shaping beauty on a galactic scale. It is strange to think that something born from collapse could give rise to such order. But that is the black hole's paradox. It is the universe's reminder that even the darkest hearts can be architects of light. There are some things the universe does not want us to see. A black hole, for instance, hides its singularity behind the event horizon, a veil drawn not out of secrecy, but necessity. That boundary protects the rest of reality from the infinite. Beyond it, the equations of physics cease to function. Space folds into an impossible curvature. Time loses its direction. The singularity is a wound in the fabric of the cosmos, and the horizon is the bandage that keeps everything else from unraveling. But what if that bandage were gone? What if the singularity stood exposed, naked to the universe, radiating its impossibility for all to witness? Physicists call this a naked singularity, a theoretical object where gravity's collapse is not contained. It's a point where space-time curves to infinity, yet no event horizon forms to conceal it. You could, in principle, look directly at the heart of broken physics, a place where cause and effect no longer hold, where information might escape from regions beyond comprehension. It's the cosmic equivalent of staring into the machinery behind reality's curtain and realizing the gears don't fit together. Einstein's equations allow for naked singularities, at least in theory. Certain solutions to general relativity, like those describing rapidly spinning or collapsing stars, suggest that, under specific conditions, the horizon might fail to form. The singularity would be laid bare, unshielded, influencing the universe in unpredictable ways. But this notion unsettles physicists. It violates what's called the cosmic censorship conjecture, a principle proposed by Roger Penrose in the late 1960s. The idea is simple. Nature hides its singularities. No observer, no matter how brave or reckless, can ever witness the breakdown of physical law. The universe censors its own chaos. If that conjecture holds, then every singularity remains hidden behind its horizon, preserving the integrity of cause and effect. But if it doesn't, if naked singularities can form, then the universe becomes far stranger than we dare imagine. Imagine a region where light bends not just around a center, but through it, where time could loop, splinter, or stop altogether. A place where determinism dies and outcomes are no longer governed by initial conditions. A naked singularity would not just defy our understanding of physics, it would undo it. The equations that predict gravity's behavior would dissolve into paradox, leaving us with a universe that could no longer be trusted to make sense. And yet, there is beauty in that fear. A naked singularity would be a glimpse at the raw foundation of existence, the unfiltered architecture of space-time. It would show us what gravity looks like when stripped of symmetry and order, when freed from the politeness of horizons. Some physicists suspect that the universe may flirt with such exposures but never commit fully to them. Like a painter who lets the underdrawing show through, the cosmos may hint at its deeper mechanisms without tearing the canvas completely. Perhaps the jets that burst from active black holes, the flickers of gamma radiation, or the strange asymmetries in gravitational waves are echoes of something half-revealed. Quantum gravity theories offer possible escapes from the nightmare. They suggest that before a singularity could stand naked, the quantum nature of space-time might intervene, smoothing infinities into finite but extreme curvatures. Instead of tearing, reality ripples. The foam of the quantum world covers the wound, preserving coherence at the smallest scales. Still, no one knows for sure. The laws we rely on, the geometry of relativity, the probabilities of quantum mechanics might be mere approximations of something deeper that reveals itself only when the veil lifts. To see a naked singularity would be to see the boundary of meaning itself. No horizon, no censorship, just the raw, unfiltered contradiction of existence. Space would twist into spirals of impossible logic. Time might fracture into countless paths, none of which lead back to certainty. It would be the most magnificent and terrifying sight imaginable. Not the destruction of matter, but the exposure of reality's limits. Perhaps that's why the idea endures. Not because we expect to find one, but because it reminds us that mystery still lives at the edges of knowledge. The universe, even in its elegance, still carries the potential for madness. Naked singularities are the whispers of that madness, the unblinking eyes behind gravity's mask. They promise revelation, but at a cost. To look upon one would be to see the truth too directly, to witness the universe forgetting its own laws. And yet part of us wants to look. We always have. Imagine drifting toward the event horizon of a black hole. According to Einstein's relativity, nothing special should happen as you cross that boundary. You wouldn't feel a jolt, a burn, or a wall. The universe would seem calm, the stars stretched into red streaks above you, your body weightless as you fell. Space and time would curve smoothly around you, guiding you inward as though down a long, slow river of geometry. This principle, called the equivalence principle, is one of Einstein's most sacred ideas, that gravity is not a force, but a bending of space-time itself, and to fall freely is to float in perfect peace. But then came the paradox that threatened to shatter that serenity. Physicists began to ask, what if crossing the horizon isn't peaceful at all? What if the smooth fabric of space-time, instead of welcoming you, ignites? This is the essence of the firewall paradox, one of the most unsettling ideas in modern physics. According to some quantum theories, a black hole's horizon could be a seething inferno of high-energy particles, a wall of radiation so intense it would vaporize anything that touched it. The graceful fall becomes a violent end, and the horizon, once imagined as a gentle boundary, becomes a place where reality itself combusts. The idea emerged from a conflict between two of nature's great principles. On one side stands relativity, insisting that space-time remains smooth for a falling observer. On the other side, quantum mechanics demands that information must never be lost. Hawking's discovery that black holes radiate energy posed a profound dilemma. If black holes can evaporate, what happens to the information about the matter they consume? If it's truly gone, then the laws of quantum physics are broken. But if it somehow escapes, then the structure of space-time near the horizon must be far stranger than Einstein imagined. To preserve quantum law, some theorists proposed a radical solution. Perhaps the information is not lost inside, but released through the radiation itself. Yet that radiation is emitted from just outside the event horizon. To encode the escaping information, the horizon would need to act like a membrane, a quantum surface capable of storing and transmitting data. But for that to happen, the region cannot remain smooth. The quantum fields there would boil, creating a blazing barrier, a firewall, and that incinerates anything crossing it. The equivalence principle would fail. The falling observer would never experience tranquility, only instant annihilation. This idea sent shockwaves through theoretical physics. It forced scientists to question which of nature's laws they were willing to sacrifice: the smooth geometry of relativity or the inviolable conservation of quantum information. Both cannot be right in their pure forms. To preserve one, the other must bend. Some physicists refuse to accept the firewall, insisting that space-time must remain continuous. They argue for a subtler reconciliation. That information could be preserved holographically, encoded on the horizon's surface in ways that appear smooth to anyone falling in. To the outside observer, the black hole radiates information bit by bit. To the falling traveler, nothing changes. Two realities coexist, and both are true. Others suggest that the horizon itself is an illusion, a kind of projection created by the interplay between gravity and quantum mechanics. In this view, there's no real surface to burn against, only the shifting boundary of perspective. What one observer perceives as an all-consuming wall of fire, another experiences as the silence of free fall. The paradox becomes not a contradiction, but a matter of viewpoint, resolved only when we accept that reality is not absolute, but relational. Still, the idea of a firewall lingers, flickering like a warning at the edge of our understanding. It tells us that the union of relativity and quantum mechanics remains incomplete, that somewhere, in the space between falling and burning, a new theory waits. Some call it quantum gravity. Others imagine it as a deeper structure, where information, energy, and geometry are all the same thing seen from different angles. Whatever it is, it will have to explain how the universe keeps its secrets while obeying its laws. If the horizon is a firewall, then black holes are not silent. They are radiant furnaces of truth, destroying and preserving simultaneously. If the horizon remains smooth, then nature is more subtle than we can yet perceive, weaving contradictions into coherence. Either way, the mystery endures. Perhaps both visions are true, each describing a different layer of reality. The way light can be both wave and particle, or how a horizon can be both boundary and mirage. The black hole might be a mirror that shows us our own limits, how far understanding can fall before it, too, burns. And so, as you imagine yourself drifting toward that boundary, maybe the truth lies not in whether you are destroyed or spared, but in the realization that the horizon was never just out there. It's within the mind, the thin line where knowledge ends and wonder begins. In the beginning, a black hole is born in violence. A star collapses under its own weight. Light falls inward, and gravity wins. For eons it feeds, swallowing gas and stars, bending the orbits of worlds that stray too near. It is the great consumer, the dark anchor of galaxies, the eternal shape in which matter forgets itself. But nothing in the universe is truly eternal. Even the black hole, that symbol of permanence, is slowly dying. Its end does not come in explosion or collapse, but in a long, silent fade, a soft unweaving of existence called Hawking evaporation. Stephen Hawking's great revelation was that black holes are not entirely black. Near the horizon, quantum uncertainty dances. Pairs of virtual particles flicker into being, as they do everywhere in the vacuum of space. Normally, these pairs annihilate almost instantly, their brief existence erasing itself. But near a black hole, gravity divides them. One particle falls inward while the other escapes. To an observer far away, that escaping particle looks like radiation, heat born from the edge of darkness. The black hole, to balance the energy taken away, must lose a tiny bit of its mass. It breathes out light. It evaporates. For most black holes, this process is almost imperceptibly slow. A black hole the mass of the sun would take more than 10 to the power of 67 years to vanish. a number so vast it dwarfs imagination. The universe would have long since gone cold and dim by then. Stars will have burned their last fuel. Galaxies will have drifted apart into solitude. Yet even across that desolate timescale, Hawking radiation persists, quiet and patient, like the sound of water wearing down stone. Each photon that escapes carries away a fragment of the black hole's energy, a fading heartbeat ticking across eternity. As the black hole shrinks, it grows hotter. The radiation strengthens, accelerating the process. What began as a whisper becomes a hiss, then a roar. The smaller the black hole, the faster it evaporates, until its end comes in a burst of pure light. A final exhalation. For a fraction of a second, it blazes brighter than 1,000,000 suns. And then, nothing. No horizon, no gravity well, no shadow. The ultimate darkness has burned itself out. What remains after that final moment is a question still unanswered. Some physicists believe the black hole's mass is entirely converted to radiation, every trace of it scattered into the cosmic background. Others suggest that something might linger, a remnant so small it can no longer evaporate, holding the encoded memory of everything that ever fell inside. If information cannot be destroyed, as quantum theory insists, then somewhere in the faint afterglow of that last light, the story of all that was consumed must still exist, dispersed but unforgotten. The death of a black hole marks not just an end, but a turning point in the history of the cosmos. Long after the last star flickers out, after the last atom decays, these black holes will be the final engines of change. They will radiate into the dark until the universe itself becomes thin and cold. In that far future, when everything else has gone quiet, their slow evaporation will be the last sound in the cosmic symphony, the final verse of thermodynamics, sung in a wavelength stretched beyond measure. And yet there's a strange beauty in that ending. The black hole, born from collapse and destruction, finishes its life in illumination. It gives back the energy it once hoarded, returning to the universe all that it took, diffused into warmth and light. It's as if, after an eternity of silence, it chooses at last to speak, to release everything it has kept hidden. The same gravity that once sealed it becomes the means by which it dissolves. We imagine black holes as endings, as places where matter, light, and meaning disappear. But their final act suggests the opposite. Nothing vanishes, everything transforms. Even darkness, when pushed far enough, becomes radiant. Someday, countless ages from now, the last black hole will fade into nothingness. The universe will be still, filled only with a faint, omnipresent glow, the ghost light of everything that ever was. In that silence, the memory of gravity's deepest wells will remain, carried by the thinnest whisper of radiation, drifting through endless space. The death of a black hole is not destruction, it is surrender. The universe, once fierce and brilliant, releases its final breath, and then it rests. Time is supposed to move in one direction, forward. Every second carries us farther from the past and closer to what hasn't yet happened. It's the rhythm of causality, the order that keeps the universe sane. But near a rotating black hole, one that spins so fast it drags space-time itself into motion, that rhythm begins to falter. The equations describing these objects, known as Kerr black holes, suggest that inside their spinning geometry, time can twist back on itself. There, the future and the past might meet, not as opposites, but as neighbors. If gravity is the bending of space-time, then a black hole is the place where that bending becomes a knot. The spin of a Kerr black hole doesn't just pull inward, it swirls everything around it in a storm called frame dragging. Space is caught in the rotation, forced to turn. Light, matter, and even time are drawn into the whirlpool. Within that swirl lies a region where the usual rules begin to blur, a place where the path of an object through space-time can close upon itself, forming what physicists call a closed time-like curve. If such a curve exists, you could, in theory, follow it and return to the same moment you departed, looping through time like a planet in orbit. This is not science fiction, at least not entirely. The mathematics of general relativity allows such solutions, and the equations themselves don't forbid them. Inside a rotating black hole, space-time becomes so distorted that up and down, before and after, lose their distinction. Time ceases to be a straight line. Instead, it becomes a spiral, curving, doubling back, forming closed loops that trace paths through both space and history. To an observer, it might seem that events are repeating, that moments are overlapping, that cause and effect are locked in a dance with no clear beginning. But even if the math permits it, the reality might not. The path that would allow time travel lies beyond the inner horizon of a Kerr black hole, past the region where light can still orbit, deeper than any traveler could survive. There, the forces grow so extreme that no material structure, no human or machine, could withstand them. Theoretically, if one could navigate through the inner horizon without being destroyed, it might lead to another universe or back into our own at an earlier time. The black hole would not be a tomb but a tunnel, a connection between moments. Yet each attempt to describe such a passage ends in paradox. If you could travel into your own past, what would stop you from altering the events that led you there? Could you destroy the very cause of your journey and still arrive? The universe, it seems, resists such contradictions. Many physicists believe that nature contains a kind of self-consistency, a cosmic safeguard that forbids paradox by preventing these loops from forming in the first place. Others suspect that quantum effects, the same strange processes that give rise to Hawking radiation, would destabilize the geometry long before anyone could make the trip. The wormhole would collapse, the curve would snap, and the dream of returning would dissolve into radiation. Still, the idea remains irresistible. The black hole's spin, its elegant violence, tempts the imagination. It offers the faintest glimmer of rebellion against it as ever. Time's tyranny. Perhaps the reason we can conceive of time travel is that, on some deep level, the universe remembers how to fold itself. The equations whisper that time and space are not separate threads but strands in the same fabric, and under the right tension, they can weave into loops. Maybe what lies inside a rotating black hole isn't a literal time machine, but the echo of time's flexibility. It shows us that causality is not as absolute as we once believed, that the arrow of time can waver under the pressure of gravity. Even if no one will ever traverse those loops, they still exist in the mathematics as possibilities carved into space-time's design. They remind us that the universe's laws are not laws at all, but patterns, beautiful, consistent, and sometimes strange enough to suggest escape. If you could fall into a Kerr black hole and survive, you might see time folding around you, light curving back in spirals, stars flickering twice, once as they were, once as they will be. You might glimpse the past through the lens of what hasn't yet occurred, a living contradiction that defies all logic but satisfies the equations perfectly. And as you drift deeper, drawn toward that spinning ring of gravity and geometry, you would feel the universe's pulse slow, then circle back on itself. It's comforting, in a way, to imagine that time, which we experience as a river always rushing away, might somewhere curl back into stillness. That beyond the horizon, in the place where gravity reigns and logic falters, the universe keeps a secret, that endings and beginnings might one day meet again. There is a place in the universe where knowledge ends, not because the answers aren't there, but because light itself can't reach beyond it. The event horizon, the invisible edge where gravity grips so tightly that even information cannot escape. To cross it is to vanish from the visible world, not destroyed, but unobservable, sealed behind a curtain, woven from space-time itself. And in a quieter, more human way, we each have our own horizons too, boundaries where understanding falters, where our thoughts, like photons, circle but never quite return. The event horizon is not a surface in the ordinary sense. It has no substance, no skin, no color. It's a threshold defined only by what cannot be known beyond it. You could cross it without feeling a thing, unaware that you've stepped into the unreachable. Yet to the outside observer, you would appear frozen at its edge, stretched and dimmed, until your image faded into stillness. Both perspectives are true, and neither is complete. The horizon divides reality not into what is and isn't, but into what can and can't be seen. Our minds work much the same way. We live surrounded by horizons, limits of knowledge, perception, memory. Each thought we have, each discovery we make, expands that boundary a little farther, but it never disappears. There's always another layer of mystery beyond the reach of comprehension. The more we learn, the more sharply defined that edge becomes. Knowledge, it turns out, doesn't banish ignorance. It outlines it. Like the glowing ring around a black hole, the brightness of understanding only reveals the shape of what remains unknown. The event horizon mirrors that paradox beautifully. From far away, it looks final, a boundary beyond which there is no return. Yet from within the mathematics of relativity, it's only a coordinate artifact, a feature of perspective. For the one who falls, the horizon isn't an end at all, just another patch of space-time, crossed without drama. The divide exists only because of how we see it. Our own horizons are like that too. The limits we mistake for endings, grief, failure, uncertainty, are often just thresholds our perspective hasn't yet crossed. From another angle, they might not be boundaries at all, but continuations we're not ready to perceive. There's a quiet mercy in that. The event horizon protects the universe from chaos, concealing the singularity within, a region where the laws we rely on no longer apply. Our minds do the same, covering their own singularities with horizons of understanding. We are not built to hold infinity. We draw lines where certainty ends and mystery begins, and in doing so, we remain intact. Behind every question we cannot answer, every paradox we cannot resolve, there lies something dense and unknowable, a center we orbit but never reach. Science has spent centuries chasing the edges of what can be known, pressing against them with telescopes, equations, and imagination. And every time we find a new horizon, it both answers and multiplies our wonder. To study black holes is to confront the purest form of that tension, the collision between knowing and unknowing. We map the shadow, but never the core. We describe the light that cannot escape, but not what lies beyond its silence. In that gap lives both our limitation and our beauty. Maybe that's the secret the cosmos has been whispering all along, that the horizon is not a barrier meant to frustrate us, but a boundary meant to define us. It gives shape to curiosity, direction to wonder. Without it, there would be nothing to reach for. The edge is what makes the journey meaningful. The darkness, what makes the light worth finding. You are not so different from the universe that contains you. Your thoughts orbit unknowns. Your questions trace invisible thresholds. There are parts of yourself you can never observe directly. Experiences that slip beyond language. Truths that remain hidden even as they shape everything you are. And like the event horizon, those unseen depths are not failures of perception. They are the foundations of it. Perhaps the most humbling lesson of the black hole is this: not everything must be illuminated to be real. Some things exist precisely because they cannot be seen. The event horizon is both veil and revelation, limit and invitation. It tells us that knowledge will always have edges, and that wonder begins where certainty ends. So we keep looking, keep asking, keep circling that invisible line between light and shadow. Because in the end, the horizon is not just out there in the stars, it is within us, shifting, expanding, always receding just far enough to keep us moving forward, chasing the glow that marks the boundary between what we know and what we still dream to understand.